Welcome to The Explainer. Today, we're diving into a pretty radical idea. What if we could make robots learn more like us? Not just by showing them things, but by teaching them the fundamental rules of the universe, the laws of physics.
I mean, really think about it for a second. When a ball's flying through the air, your brain it instantly calculates that path, and you reach out and you catch it. You don't even think about it. But for a robot, that same exact task is this monumental challenge. So why is that? Well, it all comes down to a really fundamental problem in AI and robotics. You see, we have this intuitive grasp of physics, right? We've learned it over a whole lifetime of just existing. But how in the world do you teach that kind of intuition to a machine? Especially for a complex, super expensive arm like this one. Letting it learn by just flailing around, pure trial and error, is painfully slow, wildly inefficient, and honestly, you risk causing some serious damage. It's a classic robotics dilemma, and it has been notoriously hard to solve. So to really appreciate the breakthrough we're about to get into, we first got to look at the two traditional ways engineers have tried, and, mostly struggled, to solve this whole robot control challenge. Okay, so the first approach, the old way, is rooted in classical engineering. It's all about creating this perfect, detailed plan before the robot ever even moves an inch. Think of this like giving the robot a meticulously detailed instruction manual for its own body. I mean, engineers would literally take the robot apart, measure every single component, calculate its weight, its inertia, and build a perfect mathematical model from the ground up. And here is the key trade-off. On one hand, these physics-based models, they are fantastic. They're super reliable, and they can handle new situations perfectly. But on the other hand, actually creating one is a nightmare. It is incredibly expensive, it takes months of engineering time, and get this, if you change anything, even just add a small tool to the robot's hand, the whole model is invalid. You have to start all over again. So, on the complete opposite end of the spectrum, we've got the modern deep learning approach. The idea here is, forget the detailed blueprints, let's just start with nothing, a total blank slate. This is kind of like hiring an apprentice who learns a task only by watching you do it millions of times. The AI, which is a generic neural network, has zero built-in knowledge. It just watches the data, joint positions, velocities, torques, and it just tries to find patterns. It has no underlying theory of why things move the way they do. Now, this method is flexible, for sure, and it avoids all that painstaking manual engineering. But it's also incredibly data-hungry and, honestly, dangerously naive. It is fantastic at mimicking the exact situations it's seen before. But if you ask it to do something even slightly new, it can fail spectacularly. We're talking potentially breaking the entire robot. So this has left robotics engineers with a really difficult choice. Do you go with the rigid, expensive expert that can't adapt, or do you pick the flexible but naive apprentice that needs endless supervision and just can't be trusted in new situations? Neither of these is ideal for robots that need to actually function in our complex, ever-changing world. But what if you didn't have to choose? What if you could get the best of both worlds? This is exactly where researchers from the Technische Universität Darmstadt in Germany came in with a much smarter, hybrid approach. The core idea, as they put it, is beautifully simple but just incredibly powerful. Instead of starting with a complete blank slate, what if you could give that blank slate the formula sheet for the final exam? What if you could actually give it the laws of physics from the get-go? They call it a Deep Lagrangian Network, or DeLaN for short. It's a special kind of neural network where its very architecture is built to follow the rules of Lagrangian Mechanics. And that's a really powerful branch of physics that describes motion based on energy, a core principle of our entire universe. So in other words, this is an AI that has physics baked right into its DNA. And here's how it works so elegantly. Instead of the AI trying to learn one giant messy equation of motion, DeLaN learns two much simpler things: the energy of motion, which is kinetic energy, and the stored energy, which is potential energy. It then combines those two using a universal law of physics, the Euler-Lagrange equation. And the result? You get a network that is fundamentally incapable of producing a result that violates the laws of physics. It just can't do it. Okay, so that's the theory. It sounds great on paper, but does giving an AI a physics cheat sheet actually make it perform better in the real world? Well, let's take a look at the experiment. So the researchers set up this head-to-head competition. They took a standard blank slate AI and the new physics-infused DeLaN, and they trained them both to control a robot arm. Now, the training itself was pretty simple. Just follow two smooth, repeating cosine wave trajectories at a normal speed.
And now for the real test. Because true intelligence isn't just about repeating what you've seen before, right? It's about applying what you know to new, unseen situations. So the researchers took the models that were trained at normal speed and tested them on the exact same trajectory, but at double the speed. And the results were, well, just dramatic. The standard AI's performance completely fell apart. Its error skyrocketed because it had simply never seen movements this fast before. But DeLaN, with its built-in knowledge of physics, it extrapolated beautifully. Its tracking error stayed incredibly low, and it performed almost as well as that perfect handcrafted model. Just incredible. Now, the reason for this success is that DeLaN learned a much more fundamental model of the world. The standard AI just tried to map a simple relationship between position, velocity, and acceleration. But DeLaN, it learned the underlying energies, which only depend on position. And this deeper understanding is what allowed it to generalize to any speed or any acceleration, not just the ones it happened to be trained on.
So, what does a breakthrough like this actually mean for the future of robotics and, well, artificial intelligence in general?
The crucial point here is that this leads to huge real-world benefits. Lower sample complexity. That just means robots can learn robustly from way fewer examples, which saves a massive amount of time and money on data collection. Better extrapolation means we can finally start to trust them to perform reliably in new situations. And guaranteed physical plausibility means the AI is constrained by physics, which makes it inherently safer to operate around people. And that is a huge deal. This entire approach just opens up a whole new frontier. It represents a massive shift, a move away from AI that just mimics patterns in data, towards an AI that can truly understand the underlying principles of our reality. And it really makes you wonder, if we can teach a robot the laws of motion today, what's next? Thermodynamics? Fluid dynamics? The fundamental rules of biology? The possibilities are really just beginning to unfold.